Okay, there for you. Okay, we're back. Hey, real fast, and I'll show you my face for a second. Okay, need to go over something real fast. For you guys online, there's a few students in the class now, like not a big deal. That's fine. But listen, if we're in the middle of class and you send me a private chat, everyone in the classroom can see it because of how I'm doing this. It's like on the board. You can see the screens right here on the board. So realize if you need to send me a private message, like to explain something or ask something or explain why you missed, whatever, just send it in an email because if not, everyone in the classroom is going to see it. And by everyone, there's only like one or two people. But just please realize that everyone can see the private messages because of how I'm streaming in this class. Now, I don't think it's going to be saved on YouTube or anything like that, but the students in the classroom can see it. Just want you to know it's not technically a private message because of that, and that's all. Okay, so let's get to today's lecture. First off, before I get started, are there any questions about 2.5 or the homework, the previous homework? Yeah, there you go. Are there any questions about 2.5, 2.4? Anything at all? Okay, let's get rocking and rolling. So 2.6, we're going to go over two concepts. We've already gone over one. We've already gone over the domain concept in here. That was on a previous test, the last test. Right? Domain's the very first part of 2.6. And we've just gone over it already. We'll see it in a few different ways maybe. But the main concepts we're going to go over today are combinations of functions and compositions. So combinations and compositions. So I'm actually going to start here because we've already done this from the last test, okay? So combination of functions, there's 4 different ways to combine functions algebraically. Your book goes over this on page like 289. I'm going to go over it 2 different ways. We're going to go over algebraically, we're like actually like formulaically, and then we're going to go over it on a graph, what it looks like on a graph, okay? So first off, the easiest way to go over this is with an example. Let's say we had f of x and it equals 2x minus 1. I'm just making this up. And g of x equals 3x plus 2, okay? So we have these 2 functions. And to do the combination aspect, there's addition, subtraction, or if addition, they call it sum, difference, product, quotient. So let's look at the sum. And the main thing in this section, look, the algebra is not going to be hard. The math is going to be hard on this. It's going to be the notation. We've got to get comfortable with this notation moving forward. So let's say, tape. I don't see any. You guys see any tape anywhere? Oh, okay. Let's say we're going to add these together. You would notate it in this manner. F plus G of X. Yeah, hold on, guys. I'm having mask issues on this. Okay. So if we want to add these together, all we're really doing is adding f of x plus g of x. Very straightforward. This should be extremely basic. So if we look at it this way, it would just be 2x minus 1 plus 3x plus 2. Okay, 2x minus 1 plus 3x plus 2. You add like terms and you wind up with 5x plus 1. Okay, very straightforward, not a big deal. We can add a number in there. So like, let's say we want to do, and really order doesn't matter with addition, right, with sum. So if we added a number in there, let's say like g plus f of 3, you can think of it as g of 3 plus f of 3. So like g of 3, if we look at the g function, we plug that in. 3 times 3 is 9 plus 2 is 11. We plug 3 into the f function. 3 times 2 is 6 minus 1 is 5. So we wind up with 11 plus 5. So we wind up with 16. Okay, so if we're given just the function, yeah, you just have to add the really the equations together. If you're given a number, though, you can plug the number into both and then add them together. That's fine. And notice, if I plug 3 into this equation, 5 times 3 is 15 plus 1 is also 16, okay? They all go together. It all bleeds in together, okay? Questions? Make sense? It's not a big deal. Okay. So now subtraction, the only thing you have to worry about with subtraction is order. Order matters with the subtraction. 5 minus 2 is not the same as 2 minus 5. So if we wanted to use those same functions, f of x equals 2x minus 1 and g of x equals 3x plus 2. But let's say we wanted to subtract them. To notate that, we'd say f minus g of x, right? Order matters, so we're going to have to write these out accordingly. So the f goes first, so 2x minus 1 minus 3x plus 2. So you've got to distribute the negative here to get rid of the parentheses. So this winds up being 2x minus 1 minus 3x minus 2. And we're left with what, like negative x, 2x minus 3x. Negative 1 minus 2, that's going to be a negative 3. Okay, not a big deal. The main thing is to notice the notation. So if you see that notation, all it really means is you're going to take the first function and subtract it by the second function, okay? Product, same kind of thing. Nothing crazy. It'll look like fg of x. So if you see them just next to each other, that means we're going to multiply them together, okay? So for this one, it would be 2x minus 1 times 3x plus 2, right? And then you've got to FOIL it out. So 2x times 3x, that's 6x squared. 2x times 2, that's 4x. Negative 1 times 3x, that's minus 3x. And then negative 1 times 2, that's negative 2. So we wind up with 6x squared plus x minus 2, right? Again, no big deal. Again, so mainly this is the notation. So this is subtraction. This is multiplication. And the last thing, the last kind of notation before we get to some real examples is the quotient. It's division. And I'll tell you, with division typically comes the domain question. So if I kept these same functions, a little lazy, kind of do it like that. Same functions. If I wanted to ask you to divide them, that turns out to be pretty easy. Like f of g of x, or f over g of x, I should say it like that. To divide them, you would just do the top over the bottom. Very straightforward. And this one, it doesn't simplify. So this one's done, okay? This is really easy, okay? There's no real thing going on. You just put them as a fraction. But typically with this question, you get the domain. So this should be a review, but if I ask you to find the domain of f over g of x, okay? Find the domain of f over g of x. Now remember, the domain of this function, the red flag going on here is we've got an x in the denominator, right? We've got an x in the denominator. So that means we have to state that 3x plus 2 can't be 0, right? 3x plus 2 can't be 0. If we had that, then we have a division of 0, and we can't have that in algebra. So let's solve it out and subtract the 2. We get 3x can't be negative 2 without the 3. And we find out that x cannot be negative 2/3. Now, x can be anything it wants to be, right? It just cannot be negative 2/3. So I've got to write that in interval notation. So really remember, it can be anything to the left of negative 2/3 and to the right of negative 2/3. So we would write it as negative infinity to negative 2/3. Remember parentheses because we can't equal it, okay? This is anything to the left of 2/3 or anything to the right of 2/3, right? And if you go back, if you're like, man, I just don't remember this stuff, this is the first part of 2.6 that I incorporated into the first test because it really should have been on the first test. Okay. It really should have been like section 2.1, 2.2, but your book, I feel has it out of order. Okay. So if you're like, man, I need to look back, this is the first part of the section. Okay. And I know I kind of zoomed through these, but this is basic algebra. This is stuff you really you should know. So let's look at an example though of when this is used. Combinations of functions are used a lot, especially when it comes to if you know an equation or know a model for something, or two things, you can combine them to find the combination. Your book talks about birth and death rates. It's on page 291. And it gives us a birth rate and a death rate. Now I'm going to define what X is first. X is years after 2000. Okay. So like the year 2012 would correlate to X equals 12. Okay. So X is years after 2000. So like 2012 would just be X equals 12. And it gives us the birth rate for each year and the death rate for each year. So the birth rate, B of X, they use capital B, is negative 2.6. This is on page 291, guys, if you want to follow along. But it's negative 2.6 X squared plus 49X plus 3994. The death rate is negative 0.6 X squared plus 7X plus 2412. So we know the birth and the death rate of each year, and it's presumably what's going to happen is you have more births than deaths. And if you look at page, it kind of references a graph. It's on like page 286. You don't have to have the book out, but the graph kind of shows you what actually happens throughout these years on page 286. But so we've got what actually happens versus a model of what happens. Look, these are not going to be perfect, right? They might be really close, but you're never going to get an equation that models the real world perfectly, okay? So don't ever think that's possible. You're never going to get a real equation to model the real world perfectly, but we just try to get as close as we can for prediction reasons and things like that. So let's look at this. The question says A, write a function that models the change in U.S. population for the years from 2000 to 2009. Okay, well, if we wanted the change, we would just do the births minus the death. Okay, birth minus this. And this is going to give us the actual change, the increase each year in the U.S. population, right? So it doesn't take into account like people leaving, immigrating out. But anyway, or immigrating in. So, but this is just birth and death. So we've got the births are going to be negative 2.6 X squared. I'm going to run out of room here. A little smaller. 49X plus 3994 minus negative 0.6 X squared plus 7X squared plus 2412. Okay. Now, look, I've got to subtract these. So really, instead of having to write this again, I'm going to be lazy and just say it changes the sign on all these. So this becomes addition, but then this becomes addition, and these two become subtraction, right? I distribute the negative through, and it just changes the signs. So my difference equation would be negative 2.6x squared plus 0.6x squared. So that's going to be negative 2x squared, right? You're adding off we're subtracting off the 0.6. And then 49x minus 7x, so that's going to be a 42x. 3994 minus 2412. Now I'm going to be a little lazy and just steal it from the book. Winds up being plus 1582. Okay. So we have the equation now for the differences. So this is kind of a real world scenario on the equation of the differences in this type of book, okay, or in this type of example. And then so that's part A. So that's answered A. B states though, hey, use the function from part A to find the change in the U.S. population in 2008. So hey, We want to know what's the change in 2008. Now remember, 2012 meant x equals 12, so therefore 2008 means 8, right? And all we have to do is plug it in. So we get b minus d times 8 equals negative 2 times 8 squared plus 42 times 8 plus 1,582. Now I'm taking the calculator out. See if I can put this in the calculator correctly. 2 negative times, well, 8 squared 64. I'm going to put it in like that. Plus, not times, plus 42 times 8 plus 1,582. I got 1790. Is that what the book got? That's like an important year. The book got 1790 as well. Okay. So you should get 1790. So the equation models to get 1,790, like that's the difference. So we should add, now this is in thousands, I believe. So it's really 1 million. So 1,790,000 more in population this year from births and deaths, okay? So that's the difference. Now C states, does the result in part B overestimate or underestimate the actual population change in 2008? Now, we've got to go to that figure on page 286. And if you go to that figure and you go to 2008, the actual births in 2008 were 4,247. And the actual deaths were 2,453. Okay, so this is what actually happened. Now, I said these are in million, or these are in thousands. So it's really 4,247,000 and 2,453,000. So if we look at this, if we subtract this away, 4,247 minus 2,453, we get, so B minus D here gives us 1,794. Man, that's pretty close. Okay, look at that. This is what actually happened. This is what the equation modeled. And it's only 4,000 people off, right? But it did underestimate, right? Actual change. The equation, right? This is the equation. The equation underestimated what actually happened, right? Okay. The equation underestimated what actually happened. Kind of neat. I mean, you would use these with like finding profit, right? If you wanted to find the profit of a company, you would take the revenue and minus the cost, right? And a lot of companies have like revenue equations, and they have cost equations built in to different products or services or whatever. And it's the same thing. It's just a combination of what's going on. Like, yeah, pretty cool. Okay. If you guys have more questions about that, just ask me. If you're struggling with it, I'm going to go on to compositions. I feel like students have a tougher time grasping compositions, and I honestly like talking about compositions. One of my favorite parts about teaching, because I get to hear how your brain thinks. So let's talk about compositions. So before we get rocking and rolling on what they are, I'm just going to define them, and I'm going to ask you to explain them in a real world way on how your brain thinks it should be explained. So compositions work like this. Now, to write them, you would use F, and that's a little circle, G, and that means F composed of G. Okay, so this means F composed of G. Okay, F composed of G. Now, it's not multiplication. We know how to do that already. What's different about this is that, and I'm going to bring up the chat box here. Can you guys still see that? Okay, back there? Okay. What's different about this one is that you're actually taking this G function and you're putting it into the F function. Okay, you're going to take the G function, you're going to put it into the F function. So algebraically, it looks like this. It looks like F composed of G of X. Okay, so you're taking the G function and it's inside the F function. Now, here's where I'm going to pause for a second. And I want you to think about this, really think about it, okay? Can you think of an example in the real world? Doesn't have to be math. We'll go over a mathy example here in a second. Can you think of an example in the real world where you take something, you put it into something else, and it becomes a totally different thing? I'm asking the in-class, out-of-class. Now, guys, on Zoom, you can put it in the chat box. I promise there are no dumb answers. I've heard some pretty answers that I thought were dumb. They weren't dumb. What do you think? Blender. Okay. I'm going to tell you why I like where your brain's going about Blender. But in the Blender, you kind of add things together and you mush it around and then it becomes something. Does that make sense? So it's not necessarily, it's not the worst, but it's not even a bad example. Okay. Yeah. No, I like where your brain's going. Actually, I like where your brain's going. The fact it's not with food or a drink or something, because it's kind of easy to get that with food, right? Say it again. Milk to cheese. I'm going to say it's a little different. It's hard to do with compositions because like milk turns into cheese, right? So it's not like you're adding, I know you added a few things to get it to become cheese, but like, it's not like you're adding it and then it becomes something else, right? Does that make sense? You can kind of say that. We could probably, I'm going to go over an example that kind of probably hones it in a little easier, but I like where your brain's going because I love cheese. Anybody on Zoom? Oh, here we go. A duck and a turkey for Thanksgiving. Oh, I like this one. Okay. Has anybody had a turkey or a duck inside of a turkey for Thanksgiving? It's turducken, right? Or is it? No, it's not turducken. You got to have the chicken, right? What is it called? It's got a name. Okay. But CJ, I'm going to run with this one because you kind of see how we take the duck and we put it in the turkey, right? Does that make sense, guys? Okay, so think about this. We're going to take the duck and we're going to put it into the turkey, right? Now, if we think of this, though, let's make an equation now for that. So let's have T of X. And I know this is goofy. We're just going to call it the turkey. And we've got the duck, right? Did you say turkey? Yeah, duck. We'll call it D of X. Okay, so we've got T of X and we've got D of X. Because I'll tell you, the issue students have with this isn't usually the math, it's the order. Okay, it's the order. So if I want to stuff the duck into the turkey, the duck has to come second. Okay, so if I want to put the duck inside the turkey, I've got to write this duck second. So if I'm going to write these two as a composition, it would look like that, right? This would put the duck into the turkey. The other way is probably not going to happen, right? I mean, this could be a pretty big duck, but in a small turkey. But you'd have to really, the way we think of the size of turkeys and ducks, it's not going to happen. You guys think of another one? That's a good one. Someone yesterday in the other class said a vending machine, and I never had thought of it. And they're not wrong. They were like coins in a vending machine. You put the coin in the vending machine, and then it pops out a drink. It's like, it's a kind of an interesting real world example for composition functions. And it does kind of make sense. Now, if you would do that, if you had like V of X was the vending machine, and then C of X was the coin, you know, you would write it like this. You'd put the coin into the vending machine, right? You guys think of another one? I'm telling you my favorite example, unless someone pops up on chat. My favorite example of this is a jelly donut. Because we have two very separate things, right? We've got jelly. We'll do JX. This jelly. And we've got the donut, D of X. Okay? And if we want to make a jelly donut, you really have to be careful on which one you do into what, right? If you wanted to make a jelly donut, what would need to come first here? The donut, right? Yeah, because you're going to put the jelly in the donut. Now look, donut jelly sounds awesome. Like if you got jelly and it had like pieces of donut in it, I'd eat that. I'd eat it. I'd eat too much of it. Okay. But if I wanted to make a jelly donut, I would definitely need the donut first, and it would be composed of jelly. Okay. So you take the jelly and the put it. This gives us actually the jelly donut. Okay. The other way would be donut jelly. Okay. So it's kind of backwards how we write it, right? Okay. So I'm telling you this, I know these are goofy examples and these aren't math examples, and that's not the point. The point at the beginning of learning compositions is really which order to put things in. Okay. Is putting one into the other. And to do that, you have to have a certain order to do it. Okay. You have to follow an order to do it. So let's look at a math example we've all probably kind of done at some point. I call this the coupon example. Let's say we go to a store and we've got a coupon, okay? And we've got, let's say, a $10 off coupon. So X is going to be the sales price. X is going to be the coupon function gives us the price after the coupon, okay? So let's say we've got $10 off. X minus 10. Okay, so we've got, this is the coupon function. Coupon function. Now, we have to pay sales tax, right? So I'm going to use another function to describe sales tax. Now, at Mountain Home, I think sales tax is around 9.5%. We're gonna just say it's 9.5%. So if I wanted, if let's say I didn't have a coupon and I went in and bought something, if I wanted to know my total, I just have to really multiply it by whatever 9.5% is and then add it to the total. So a quick way to do that is just multiply 1.095 times X. Okay, so like if we bought something for, like $100, it'd wind up being $109.50, right? So this is a quick way to get the tax. You just add a 1 here, 1.0, and then whatever the tax is. So this is our tax function. Okay, this is a tax function. And we're going to think of actually how we would do this in a store. Now, the thing about the store is that, and this is what typically happens, you take the coupon and you just pay the tax on afterwards. Now, there are some things that you have to tax the entire thing, even if you use a coupon. But for our example, we're only taxing the amount after the coupon. Okay, so if it's like $50, we're only taxing the $40. Okay, so let's think about this. If I go to a store and I find something for like $90, right? Well, it's not going to go into the tax function first. It's going to go into the coupon function, right? I'm going to take the $10 off, so it's 80, right? And then I'm going to take the tax of $80. That's for my total, right? This is, I should say tax function, it's like total tax function, okay? That's the total with tax. So to write that though, we got to think about this. So first, I actually have to take the coupon value and then I'm putting it into the tax function. So to do that, I would write it this way. Now remember, coupons going into tax. So tax actually is written first, but in a way it is second, right? So it's T composed of C of X. It's T composed of C of X. So I'm going to show you here algebraically how to do this. So this is the algebraic side. A really kind of good basic example of the algebraic side of compositions. So we have our two functions. And all we're really doing, if we write it this way, we know, just like the jelly donut example, we're taking the coupon and we're putting it into the tax. Now, what that means, I'm going to show you the long way to do this, but because if not, the math gods come down and they score me. But then I'll show you the short way, okay? So the long way looks like this. You'd actually take T of C of X, okay? T of C of X. This is where it's coming from. And so then you would have t, now you have to go inside to outside. So you'd have t of now, this c of x is written as x minus 10, right? We know that. It's defined right there. It's x minus 10. So you have to replace the c of x with the actual equation. And look, we know how to do this. Remember that introduction to function section? We went over ones like this, where you just plug in x minus 10 into the t function for us. We're going to plug it into this one. So we wind up with 1.095 times x minus 10, right? We're just taking that, putting it here. Now I'm going to distribute this. And we wind up with 1.095x minus 10.95. This would be my composition function. This would be t composed of c, okay? This is the long way to do it, okay? It's a long way to do it. And again, if I didn't show you this, the math gods would come down to me and get on to me for not showing you. But look, here's all we're really doing. All we're really doing, since it's t composed of c, we know that that means c goes into t. All we're doing is taking this c function and we're putting it into the x value of the other function. Right there. Okay, that's all we're doing. We kind of skipped this first few steps. Now, we'll see some goofy times when we have to come back here, but we'll get to that in a little bit. So don't worry about that. But for now, I need you to grasp this concept. All we're doing is putting the second function into the first function. That's it. Now, what's nice though is we have an equation now. If we know the total price, we just pop it into here. And in Mountain Home, if you got a $10 off coupon, you can get the price you're going to pay. So like, let's say we go somewhere. Is Stage still open? They used to be my go-to coupon spot. TJ Maxx isn't a coupon. Let's do TJ Maxx anyway. Let's go to the Max. Okay. We go to the Max. I love candles. Okay. And TJ Maxx has the best freaking candles. So let's say I go to the candle section and I find an overly priced candle because that's all they really have. And this candle turns out to be $37. Okay. But it smells delicious. And I want to know, well, what am I actually going to pay? Right. Now, of course, I know you're thinking, we'll take $10 off and then just add the tax. And you're right. That's fine. But I've got an equation here that'll give it to us in one step, which is exactly what how the registers are computed, how they program for the registers. This is what they do. It's a lot easier to program a single equation than two. So you get 1.095 times 37 minus 10.95. I'm going to take my calculator out and I'm going to say, okay, clear this up. So I've got 1.095 times 37 minus 10.95. 29, I'm going to round it to the penny. 29.57. So that's the amount I wind up paying. Now I'm only really, I know I have a $10 coupon, but Uncle Sam's got to get his. So I wind up saving about $7.50. Okay. Makes sense? Kind of neat. Okay. Real world example. Another one. So let's do some that just aren't real world examples, but we just got to get the algebra down. Steal some in the book here. Actually, yeah, I need to steal some in the book because they go over the number too. Let's look at let's say 54 in the book. This is 54 on page 298. And all of these are going to have an ABC component, okay? So 54, the two functions are f of x equals 5x plus 2 and g of x equals 3x minus 4. So here's what I want you to do. I want you to find try this on your own, f composed of g of x. It's okay if you get it wrong. That's why we're doing it in class. And then I want you to find b, which flips it around. g composed of f of x. So try those two real quick. See what you get. Okay, keep working. Let's see. And again, I'm going to do this the short way because I know now that all I have to do is put g into f, right? So I'm going to take this g function for part A, and I'm going to put it into the x function for f. So this winds up being 5 times 3x minus 4 plus 2, right? Now distribute the 5. I get 15x minus 20 plus 2. So I wind up with 15x minus 18. Okay. And then you're going to do vice versa here, right? For this one, you're going to put f into g. So I'm going to take the g function and I'm going to put that into, I'll take the f function and I'm going to put that into my g function. So I wind up with 3 times 5x plus 2 minus 4. So I wind up with 15x plus 6 minus 4. 15x plus 2. Okay? Questions? Not too bad. We've already done some good examples of it. Are there any questions? So I'm going to just choose part C here to show you. It's kind of nice when you have the equation already for part C. So part C says, what's f composed of g of 2? Now look, I'm going to show you how to do this without the equation here in a minute. But we've already found the equations right here, right? F composed of g of x is just 15x minus 18. So we just have to plug 2 into that equation. So 15 times 2 minus 18. So 30 minus 18. We wind up with 12. Okay, so you just have to plug the x value into the equation you have already found. Okay? Questions? Too bad, right? It's really not bad. It's not bad because we're understanding the order. The order winds up being the goofy part. The math isn't too bad. I mean, the algebra aspect isn't bad. It gets a little, more complex down the line, but it's not too bad. So let's look at one where I don't ask you to find the equations and I just start with a number. Let's say I said g of x is equal to x squared plus 3. And let's say h of x is equal to 2x minus 4, okay? But instead of asking you to find the composition of x, let's say I ask you to find G composed of, H. G composed of H of, let's say, 3. G composed of H of 3. Now, this is what's different because you don't take the 3, excuse me, and put it into both equations. This is when we really have to think of how it was, how I defined compositions earlier. Algebraically, remember, this is defined as G of H of 3, right? Is G of H of 3. So we need to write it like this, and we're going to work inside out. Okay, we're going to work inside out and find what's on the inside and then keep going. So look, first we've got to find H of 3. H of 3 is not bad. I've got my H of X function here, right? If I put in 3 into this function, I get 3 times 2. That's 6 minus 4. So it turns out H of, wait, 6, that's 6 minus 4, that's 2, right? If I plug in 3 here, 3 times 2 is 6 minus 4, that winds up being 2. Okay, H of 3 gives me 2. Well, then I've got to plug that G of 2 into this equation, right? I mean, I know how to do this. We've been doing this for a little bit. So I'm going to take the G of 2 and I'm going to plug it into here. So we wind up with 2 squared plus 3. So 4 plus 3, we wind up with 7. Okay, we wind up with 7. I'm gonna give you an example on how to work, or I'm gonna give you an example. I want you to kind of work this one on your own to see if you got it. And I'm gonna change the order up. Let's say I ask you to do G of, or H of G. Let's say the same thing. Let's say, I should write it a little lower, but H of G of 3, looks like Holland. H of G of 3, try that one, H of G of 3. Okay, let's see. Let's just look at the order here. So again, I'm going to write this as H composed of G of 3 now, right? I'm going to start with the 3 going into the G. Well, let's find that. So G of 3, I go to the G function now and I put in 3. 3 squared is 9 plus 3 is what, 12? So we wind up with H of 12. And then H of 12, I just go to the H function. 12 times 2 is 24 minus 4. Winds up being 21. Not too bad. All right. You guys got it? Questions? Did I do math wrong? What should it be? Oh, it should be 20. You're right. Sweet. Yeah, it's 20. You're paying attention. I was just checking. Okay. Questions, guys? Comments? Not too bad. Okay, good. Let's throw some trickier equations out there and just test our skills here. Okay. Let's say, let's look, man, 64, this looks rough. Let's see what happens. 64. 64's got f of x equals 6x minus 3, and g of x equals x plus 3 over 6. Now, I'm not going to ask you to do all A, B, C, and D. I want you to do A, which is f composed of g of x. And then I want you to do B, which is, I'm sorry, not B, but D, which is G composed of F of 2. Okay, so you find the equation for F of G. And then this one I want you to do that way we just did, right? F of 2 and then so on. So try these two and see what you get. Okay, I'm gonna start with the first one. So this one, we've got to put G into F, right? Okay, so we're gonna take this entire fraction here, and then we're gonna put it into that X value. So we wind up, now I'm gonna write this kind of big, so we wind up with 6 times X plus 3 over 6 minus 3. Okay, this is kind of nice. Because look, this 6, I mean, if you multiply an integer by a fraction, you really just multiply the entire top by the fraction. But what's nice is it's the same factor in top and bottom. So this 6 cancels. So we wind up with X plus 3 minus 3. And then the 3's cancel. So we wind up with just X. Okay? Kind of crazy. Okay, we wind up with X. So we put in the G into it. Now this is a special, these are two special functions. We're going to talk about them more in the next section. But we wind up with X once we simplify everything down. Okay? So now let's go down here and do the same thing. Okay, so if I've got to write this one, I don't know the equation for this, right? I know the equation for F composed of G. I don't know the equation for G composed of F. So I'm going to write this like we did earlier. So G of F of 2. So I'm going to first find F of 2 here. So I'm going to go to the F equation. 2 times 6 is 12 minus 3 is 9, right? And then I've got to go to the G equation and plug in 9. So if I plug in 9, I wind up with 9 plus 3 over 6, right? Into this equation, which winds up being 12 over 6, which winds up being 2. Okay? For this example, it's not a coincidence that these two are equal to each other. Okay? And we'll go over that more. I'm not worried about, actually, it's a whole section. We'll talk about it for an hour and 15 minutes in the next lecture. But this is the math behind it. So I'm glad that your book kind of put in a little bit of the algebra. So the algebra part won't be new when we get there. It'll just be the concept of what happens when this occurs. Okay? Questions? Guys, questions on the Zoom before we get rocking? Actually, we're not far from being done. I'll tell you, the last few parts here I'm going over tend to be the hardest to conceptualize for students. And it has to do with the graphs. Like, what if I don't give you an equation? Does it mean that it's a straight line on a graph? Well, we'll get to it, CJ. We'll get to it. Sit tight. Come back tomorrow or come back on Tuesday. We'll talk about it. But let's talk about the graphs now. If you were given a graph and you were asked to do these, actually, hold on. If you look in your book here, zoom in. This is some old school zooming in. We're going to go to your book. It's on page 298. Okay, on page 298. Let's see if I can do this. Oh, that doesn't bend. Probably shouldn't do that then. Page 298. Let me get this in focus. Boom, right there. Okay, so notice on page 298, we'll do the even. Now I've got the answers already because this is a teacher edition, but we're going to try the even ones here. Now we're back to combination. So we've got these two functions. We've got the blue function is the f function and the g function is the red function, right? So I'm going to try 84 here. I wonder if I can kind of get it in the picture. That's kind of hard. Okay, I'm going to try 84. So let's do 84 real fast. So we look at 84. We're finding g minus f of -2, right? G minus f of -2. You notice like it's way too, I've zoomed in too far now. I can't really do this, but remember with combinations, that -2 goes to both equation or both functions, okay? So you wind up with g of -2 minus f of -2, okay? Boom. You wind up with that, g of -2 minus f of -2. And so really, we've got to look at the graph now and determine what's g of -2 and what's f of -2. Okay, I'm going to write it. We'll write it over here. Hard on the hard surface, but we can look at this graph and find this. Remember, the g function is this red function. Now, the x value is -2, right? So all I've got to do is go to the x value of -2, and then I've got to go up and find the y value. Boom, right there, +2. Okay, so this equals a +2. Minus, now I need to do the same thing for f of -2. So remember the -2 is the blue function, right? And the x value I'm putting in is -2. So I need to go to -2 and then go up. And my y value is +3. So you get 2 minus 3, you get -1. Okay? You wind up with -1. So I'm going to use this graph, and I want you to find a different, it's not in the book per se. I'm going to make it up. I want you to find f plus g of, let's do f plus g -3. So I want you to try that one, f plus g of -3. So it's an addition. Try that. I'll give you a few seconds to work on it. We'll go over it. It's not bad. Once it clicks, right? So all you're really doing is f of -3 plus g of -3, right? So we've got to go, now remember the f graph is this blue one. So we've got to go to -3 now and go up. Oh, we're at 4. So f of -3 is 4. Plus, if we go to the red graph, that's the g graph, right? G of -3 is going to be a +1. So hey, 4 plus 1, we know that. That's +5. Okay, makes sense? Same thing like if it was f times g of -3. You would just do f of -3 times g of -3. You'd wind up with 4, right? 4 times 1. Okay, So now let's look at the composition side of those. So the next graph down is composition, and actually it asks you for various compositions. Try to get this at the top. Moving everything around. I'm sure something's gonna fall off. That's not gonna work. Okay. So we've got now this graph, and it's asking different compositions for this same kind of idea. So let's look at 92. 92 states F composed of G of 1, right? F composed of G of 1. Now, before I look at the graph, I'm going to write this like we have been algebraically, because we don't have an equation here, right? We just have the graphs. So this would be F composed of G of 1, right? F composed of G of 1. So now, just like before, I've got to work inside out. I've got to find the G of 1 first, find what that is, and then find F of whatever you find out what G of 1 is, okay? So let's find G of 1. Okay, G of 1, this is our G function. Go to positive 1. Ooh, it's way down here, right? Negative 5. So F of negative 5, okay? Now I'm going to switch over to the blue function because the blue function is the F, right? F of negative 5. Ooh, so now I got to go over here at negative 5 and go up and wind up with positive 3. I wind up with positive 3, right? So F of G of 1. So first, and this is really what composition functions do. It takes y values of the second function, and they become x values in the outside function. So the inside, outside, think inside, outside. The y values of the inside function. So G of 1, 1's the x, right? Down here, negative 5 is the y. It takes the y values of the inside function, and they become x values of this outside function, right? The outside function. Remember that we're going like that, okay? Question? Kind of tricky because there's no equation. Kind of different, but that is how it is. Okay, so for homework, let's kind of zoom out here. Give you a little motion sickness. Okay, for homework in this section, this is on page 297. Let's do 31 through 43. And then we're going to skip down and do 51 through 65. All of that is odd. But then I want you to do, we'll do an example like 75 before we leave here today, okay? So I need to do one of those. But I want you to do 75 through 86. And I want you to do all these. These don't take that long. There's not a lot of algebraic process to them. It's just noticing stuff on the graph or in the function. And then 91 through 94. So we'll do all of those. Those are going to be important. And then 97, 99, and 101. Okay, so that's the equation. That's on page 297. It's section 2.6 homework. Okay, now before we leave though, we have a little time. Let's talk about these where I give you a composition and I ask you to find the two functions that are composed of it. The way this looks is it says, okay, let's say we got h of x, and we know that h of x is f composed of g of x. Okay, we know that it's a composition function already. And it turns out h of x equals something. I'm going to make one up, like 2x minus 3 squared. Okay. And we've got to determine now what f of x is and what g of x is. Okay. But what's different is we're giving the output, right? We're kind of given the composition. And we need to think of these as inside and outside functions. If you're planning on going on to like a calculus class, you're going to need to know this, like business cal or cal 1. This is going to have to be like a tool in the toolbox kind of thing. So remember, the G goes into the F function, right? So if we look at this, we've got an inside function here. You guys see that 2x minus 3? That's going to be considered my inside function. So inside is G. So I'm going to write that down. 2x minus 3 is going to be my inside function. Now, if 2x minus 3 is my inside function, think if I want to create this equation, I've got to plug it into x squared, right? If I plug this into x squared, I would get 2x minus 3 squared. So these are my two answers. It's two answers really on these functions. Okay. Okay. So let's do another one. Let's say we've got h of x, same thing. H of x equals f composed of g. Okay. But now our h of x is, actually, hold on. H of x is 1 over x plus 9. Okay. 1 over x plus 9. And I want you to find f of x. And I want you to find g of x. Okay. So for this one, and jot it down, jot down what you think it is. But you got to think, like, really, you start with the inside function. Well, the inside function here is this entire denominator. Okay. That entire denominator is going to be my inside function. So that's going to be x plus 9 for my g of x. Now, if that's my entire inside function, I would plug it into 1 over x, right? If I take this and plug it into here, I'd have 1 over x plus 9. This would be my two functions, okay? Okay, that's like 75 through 82. I just wanted to go over a few examples of that. Okay, we're getting done a little bit early, which is fine. Do you guys have any questions? I'll leave the homework up there. You guys have any questions? Makes sense. I want to go real fast, just look at the schedule to make sure to see where we're at. If you guys ever need to get to Blackboard and the portal's down, if you search Blackboard ASU Mountain Home, there's a link there. It's ASU Blackboard, which is kind of nice because yesterday, I guess the Blackboard, the portal was completely down. These are Tuesday, Thursday. Schedule. Okay, great. So we're a day behind, right? So this is, are we a day behind? That was 2.6 and we're week 5. Yeah, we're a day behind. So what we'll go over 2.7 on Tuesday. We'll review. So the test will be next Thursday, starting next Thursday, and then it'll be open, until Sunday. Okay, great. Questions, comments, concerns? I will see you all on Tuesday. Enjoy the weekend.